First of all, I want to thank organizers for the invitation to give a talk. This is a very good opportunity. Well, really, this is some kind of draft or sketch of few approach to the theory of mapping bounded distortion. And this approach, I think that it generalizes all approaches what exist in the literature. I would like to give a definition, connection with classical definitions, and then to formulate some properties and applications of this class. Very good. Then, first of all, definition of Sobolev class space. So Sobolev function has the first generalized derivatives, and these derivatives are integral to the power p, and with this well, this is very strange story. Was well, but I think that this definition is known, and I'm not going to stay in this place for a long time. And I gave the definition because it will in my talk. I'm mapping D. We consider a Euclidean space Rn and a domain D. And the mapping phi belongs to Sobolev space. It means that all coordinate functions belong to Sobolev space, and then a homeomorphism phi from D to D prime is said to be quasi-conformal if it belongs to Sobolev class, and there is an inequality between norm of differential to the power n and Jacobian. This inequality means that Jacobian is supposed to be non-negative, and moreover, there is a geometric sense of this definition. It means that this differential as a linear map, it transforms a unit ball to the ellipsoid, to an ellipsoid, and the ratio between the largest semi-H and the smallest semi-H is controlled by a constant K. And this constant K is the same for all point X. Then I give another definition. Another definition requests concept of adjoint matrix, and it is connected with the given matrix with this equality. If determinant that does not vanish, and it is extended by continuity in the topology of Iron device. And a homeomorphism phi from D to D prime of Sobolev class intermu11 is said to be quasi-conformal if this inequality holds almost everywhere. And what is the definition? What is the difference between this definition and previous one? If Jacobian equals 0, then in the first definition of partial derivative range. But in this case, if at the point x determinant equals 0, then all minus of the order n-1 equals 0. In some sense, it's not the same property. But what is interesting is that in spite of this difference, these two definitions are equivalent. It means that if mapping is common in the first sense, it will be also common in the second sense. Starting from this definition, I will omit all intermediate steps to give the following definition of operator distortion function. In the classical literature, the first definition is called Auto definition of conformality. This is Auto definition. And this definition is called Ine definition of conformality. And what is interesting that the first definition is responsible for the properties of the inverse mapping. And the second definition is responsible for geometric properties of the for the given mapping. And starting from this definition, we give some kind of generalized concept of Ine operator distortion function. It is given for mapping of Sobolev class W11. It is supposed here that I will consider not only homomorphism but also some kind of more general mappings. But the own definition can be given for an arbitrary mapping type. And it belongs to Sobolev class. And the Ine operator distortion function is defined by this unusual way. Here, theta is some kind of weight function. It is supposed to be here strictly positive almost everywhere, and it is finite almost everywhere, and it is locally integrable. Then it's clear that if this function is identically equals 1 and p equals to n, then we have definition given in the previous slide. And but what is zeta? Zeta is a set of points where the cogwheel vanishes. Then K is calibrated. Then we have Auto operator distortion function. It looks like in this slide, and K is usual K, and then omega is also some kind of weighted function, and S and A is connected in this inequality. From the first look, it's very hard to say how this definition can work. And to explain this idea, now I connect all the definitions in one theory. Well, the theory is the following. We have three conditions. Phi is homomorphism, belonging to this Sobolev class. Phi has finite co-distortion. It means that adjoint matrix vanishes almost everywhere on the set zeta. And this distortion function is equal to the power rho, where rho is defined by this quality. We have these three conditions. And what can be derived? Why do we need this kind of homomorphism? Look at this. We have this space of differential form of degree n minus 1. And these forms are supposed to be integral in this power, to the power p over n minus 1. And we have pullback operator from this spatial differential form to this spatial differential form, and differential forms defined on the domain omega prime are transported to the differential form on the degree n minus 1 defined on the domain omega. And this Lebesgue space has to be calculated with respect to this weight. And if homomorphism phi has the three properties, then this pullback operator is bound. Well, then this is the next property. The inverse homomorphism belongs to this Sobolev space. The connection between S and P is given this equality. Then the inverse homomorphism has finite distortion. It means that all partial derivatives vanishes on the set zeta prime. Zeta prime is the set where Jacobian of the inverse mapping vanishes. Then determinant of the inverse mapping vanishes. And the distortion function of the inverse mapping belongs to L rho on omega prime, where rho s is defined in this inequality, omega is the integrated function. Moreover, the inverse homomorphism induces a boundary operator of these Sobolev spaces by decomposition of. And what is interesting, this the norm of this operator is bounded by both norms for the inner distortion and for the outer distortion. Norms of these two distortion functions. Well, what does it mean for the theory? This theorem really motivates the following definition. The following definition. Well, to explain what is right the definition, I recall classical definition of mapping with bounded distortion given by Krishnak 50 years ago. Then what we have mapping phi from omega to Rn. It belongs to Sobolev space W1 log omega, and we have the inequality, and between the norm of differential to the power n and between the and it is not supposed to have some topological properties for the mapping phi. And the beautiful result of Reshetnyak says that having with these properties, mapping phi is really continuous, then it is open and discrete. Very good. But it's possible to prove the result only in this case when we have power n coinciding with dimension n of Euclidean space. In the general case, we have here family of mappings depending on two real parameters. Parameters -1 and infinity. And what we need to request for this method is to be continuous, open, and discrete. Then it belongs to the topological properties. Then F belongs to sovereign class W1Q. The Jacobian is non-negative almost everywhere. Then mapping has defined co-distortion, and the function of the local theta weighted cube pay distortion, this function, belongs to this, it is integral in the power rho, where rho is defined by this equality. This is the definition. And what is interesting, what properties can be derived starting from this definition. I want to say that really almost all properties we can derive. If, for example, if in this definition, if theta equals 1, if theta equals the identity equal 1 and p equal q equal n, then all results prove in all monographs devoted to making result distortion can be proved for this class of things. Then, but what is interesting here that really, when in this case, when p equals n, this numbers are equal between and I equal to n, this case is known, and what is interesting, why do we need these two parameters families of matrix? And I want to give an answer to this question. Well, this is very strange because I had this. Device is lost. Yes. I forgot that I have. Then there's some kind of inequality, and the inequality is the same as in the theory of polyconformal methods, and almost all geometric properties can be derived from this inequality. It is called capacity inequality. Then I formulated here some generalization of very known theorem. There is a generalization of Valence theorem, and there is also some kind of generalization for these properties of this family to be known. And what I want to mention now is only the following, that many years ago, John Ball defined this class of mappings to resolve variational problems in nonlinear elasticity theory. And for his, what is interesting? It is interesting that instead of this class of John, we can consider this class. Look at this, p equal to n. Weighted function r equal to 1, and then q is between n minus 1 and n minus q, because written here, q more or equal than n minus 1. Q, it is here. And what is interesting is it's interesting the following, that this ball, this class of ball, this balls class, is contained in this class for some q. It is maybe different from this q, but it means the this class is contained in this class. And from the one side and from another side, there is also approach given by Van Jessen only. And their class is coincide with this, it is exactly this class of methods. And what does it mean? But you see that we have here some kind of distortion. And this distortion depends on parameter, linear parameter Q. And when we have hyperelastic material, we can choose an appropriate Q to resolve some kind of this is equilibrium state for the material. And the theorem said that if we consider, if we find this external deformation, it also belongs to the same class. Well, this is all what I want to say today, without any details, but it is only to give some idea what is a new class and why do we need to this class for application. Nothing more.
Thank you. Any question?